Hi, this is a lecture video on Chapter 2 from Quantitative Chemical Analysis, and it covers the topics of tools of the trade. So we're going to be discussing the various types of tools that are often found and used in an analytical chemistry lab. You have the learning objectives here, and most of these we'll talk about in the notes with the slight exception of the last one, which will be covered more in depth as we go through problem sets, as we work on lab materials. This one will be addressed during the semester rather than in the notes proper. All right, so first let's start with chemical waste. Of course, we want to begin this semester and every course, and we want to continue to develop a sense of chemical safety and chemical awareness, and we just want to make sure that the waste that we're handling, we're doing in an appropriate way. And not just waste, but that we're operating in ethical and safe ways within the laboratory. So I want you to take a moment, and I want you to try to list just 2 unsafe and 1 unethical lab practice. So thinking about the differences between those. List those here. I have a list myself that I'm going to go through in a minute, but I'm going to ask you to pause the video and try to list those, and then I'll discuss them in a moment. All right, so I don't know if you have these included, but I'm going to go through a little bit of a list. We need to talk about things like labeling our chemicals properly, sewering waste. So if we're not labeling our chemicals, it may end up in the wrong place. We could be putting waste down the sewer that should not be put down the sewer. Of course, some waste is very safe to do that with, and so we need to know the difference between that. Eating or consuming chemicals in the laboratory, of course, is not acceptable, is not something that's safe to do. Potentially not wearing goggles or not wearing a face shield, not wearing appropriate clothing that we talked about in lab. Pipetting by mouth, which I know is something that's a little bit humorous, but all too real for individuals that are a little bit older, who used to use this practice. It was quite common just a couple of decades ago. And then also, sometimes there's chemicals that are unsafe to smell. They might have adverse effects on the skin in our nose. They might be poisonous. There might be other reasons. So these are just a couple of unsafe practices. You might have a couple more to add to the list. Things that are unethical would be including putting heavy metals down the drain. So this would be something that we know is a chemical waste that is not appropriate to put down the drain, and it wouldn't just be something that is heavy metals, but stuff that we know is a pollutant or we know is a carcinogen, we know shouldn't go into the waste stream and should be collected separately. When we have knowledge of that, it doesn't just make it an unsafe thing to do, it makes it an unethical thing to do. In addition to that, random experiments in the laboratory. So just doing things that aren't described, that aren't approved, and that aren't necessarily safe. It doesn't mean that they're unsafe. So hopefully we can see here that just because something's unethical, it doesn't make it unsafe, and just because something's unsafe, it doesn't make it unethical. But these 2 categories do overlap at times. All right, so some of the technology we use in the lab. Hopefully you'll notice that there's an antique balance in the analytical chemistry lab, and it operates on basically the same principle that we see here in the upper left. So older balances that were analog versions used a seesaw structure where you would have a counterweight and a sample, or your particular material you were trying to weigh. And you would use the counterweight to get to a rough weight, and then you'd use removable weights, much like those old style scales that you maybe used at the doctor's office where they would adjust a weight over a cantilever arm. You adjust that to get close, and then eventually you arrive at a mass where they're equivalent, and you can tell the difference between those. And so they operate in interesting ways, and I hope you have an opportunity to examine the one that's on the shelf in the analytical lab, not so much because it's a technology we're going to continue to use, but because it's incredibly advanced and gave very, very good measurements. The balance that we have, I'm told, was a top-of-the-line balance from roughly the 1950s. Now, the modern electronic balances that we use electronic circuits, of course, and they actually have an internal calibration mass, and they use a current of electricity that's passed through a coil of wire, which is also known as a solenoid. That coil of wire, when electricity is passed through it, generates a magnetic field, and that magnetic field forces a permanent magnet that's within the magnetic field to move. And so depending on how much current you apply, you can get that permanent magnet to move up and down in the field. And you can measure the amount of current it takes to maintain the balance arm at a level position. And then you know, based on the mass of the internal calibration mass, you know what mass that must be. So that's how these digital analytical balances that we use, that's how these work. And they're very precise pieces of instrumentation. They're very expensive pieces of instrumentation, but something that offer us a lot of practical application nonetheless. When it comes to the balances that we use, they are, as I said, they're very, very good balances. And so we have a couple of things that we need to worry about. First is temperature. And as it turns out, as I mentioned in our calibration of glassware lab, we aren't supposed to be weighing and collecting masses on objects that are hot. If we do that, we can actually have thermal currents that are created around the sidewalls of the container, and the amount of wind that that generates will actually cause incorrect mass reading. So we want to make sure that the objects we're placing on the balance pan are as close to ambient temperature as possible, or we should expect to see deviations from their true mass. In addition to that, as masses get too high, they can actually start to damage the internal components of the balance. Though oftentimes when we're dealing with things coming out of a drying oven, it's not damage to the physical balance that we're worried about, it's just bad data. Another error we can run into, it deals with linearity. And so when we calibrate our balances, they're done at discrete masses. Somebody will come into the lab and they'll bring in a set of calibration masses, and they'll go through and they'll calibrate it to be accurate at those individual values. But as you can see at the plot on the right, which depicts at 0, 0 and at 200 mass, depicts two adjacent calibration masses, you can see that the ideal response is the dashed line is linear, but the actual response is somewhat alinear. And so the deviation from the ideal response is what we call the linearity error. Now, we're not going to deal with this in our lab. I'm not going to ask you to quantify it. I'm not going to ask you to calibrate the balances. But it is something interesting to just bring to mind and be aware of the fact that there's all kinds of errors that our experiments are subject to every day that we walk into the lab. So keep that in mind throughout the semester. Another issue that we can run into, and we are going to deal with, we're going to do some calculations with this, is buoyancy. Now, we all know that Archimedes discovered that things could float, and that the amount of volume that they displace and the mass of that volume was equivalent to the mass that they could be and still float. And so the equation here is the buoyancy equation, and it allows us to solve for the real mass of an object if we have the measured mass and then a few densities. So these rho symbols that I've used here are the densities of air, the densities of the calibration weight, and the density of the sample. And we can follow this through. In fact, I'm going to do an example here where we are measuring the mass. We have a measured mass of 100 grams. We see that we have the density of air, we have a calibration weight mass, and we filled out the equation here. We end up with a real mass of 100.08 grams. It's a small deviation, but a deviation nonetheless. And the interesting thing is to note that, this might occur if we have a sufficient body of data on this 100-gram mass. This might occur within our error. So it might be that this deviation is larger than our standard deviation, or in that same region of certainty, and so we might want to take it into account. Some other lab equipment outside of the analytical balances that we use, sometimes we'll use various types of filters. This is a Gauche filter, and they use a porous glass membrane in them that's actually welded into it and not replaceable. And these are very, very good filters. We use vacuum to filter them. So as you can see next to that, we use a suction flask, as they call it, or a sidearm flask, as they're often referred to. And we place this on a funnel with a rubber adapter so that we can actually draw a vacuum through that upper funnel, and we can use that to filter. We have volumetric flasks. We have micropipetters like the digital one we're using for our first lab. The burette, of course, we're using a Class A burette, and we'll discuss best ways of reading burettes when we get to titrations. syringes, transfer pipettes, and more pipettes. Notice that the transfer pipette contains a specific volume. The more pipette, you deliver volumes between graduations. We also have desiccators and vacuum desiccators. These are containers that we'll each have access to when we need to keep samples dry and away from humid air. This is just a short list of some of the more specialized equipment that we'll run into this semester, but important stuff to be familiar with. So, as I mentioned, we're working on this lab calibration of glassware, and in the second week of the lab, you're actually going to calibrate a volumetric flask. In fact, you're going to calibrate a 500 milliliter volumetric flask, just like the one that you see in the illustration here. So, the scenario here that is laid forward is that a solution was prepared, but it was prepared in cooler temperatures. So let's say the heat was shut off one day, or was set colder because maybe over Christmas break nobody was around, and so they decreased the temperature of the buildings. But you happen to prep a solution that day. You come back in the summer, and even though the air conditioning is running, it's still a little warmer in the building. And so there's a difference in the temperature. Even though that solution was prepped and then not used, something has changed there. Its volume has changed. So we have on the right the densities of water according to each of the temperatures between 10 and 30 degrees Celsius. And what you'll notice is that each of those densities has a significant number of certainty to it. So this is a good table to go to, a good one to maybe stick a post-it note on or a little marker out of your book, because we're going to want this in lab at some point. In addition to that, then, you see that we're reading the meniscus properly with the bottom of the meniscus at the mark. So in the equation, we have the concentration at temperature 1, we have the density at temperature 1, and then we can solve for the concentration over the density at the other, knowing that we potentially can get, for instance, the density from this table below and solve for concentration. So in this particular case, we're going to see this calculation through, and we're going to solve for C prime. We fill in the values for concentration, for the density at the other temperature, for the density at this lower temperature, and we solve for a new concentration of 0.03141 molar. You'll notice that it's not a huge deviation from the original, but it is a slight deviation. So how big is that exactly? Well, if we calculate it, it's a 0.16% change. So relatively small, but again, this might be significant in the context of the work that we're doing, and it's something to keep in mind as we're working through some of our experimental procedures. Finally, as I mentioned, Microsoft Excel is a tool that we're going to use extensively. I'm going to teach you new functions. We're going to learn about some add-in software we can use with Microsoft Excel. And I'm hoping that at the end of the semester, it's software that at the very least you feel much more comfortable with, and something that you look to outside of chemistry or science classes as something to use that's beneficial to you. So as I said before, we're going to use this pretty extensively in lab and in lecture, and I'm not going to address it here in this video. Now that concludes everything I have from Chapter 2, but we'll continue to talk about this in class and make sure that we all understand it well.